Yep.
Okay, so experiment number 1, we're looking at changing the size, the area of plastic discs here. And here, if you look, we have an airflow that is laminated. It goes through this straw. So we're looking at air flowing in lines, pushing at an area. A drag force should be proportional to the area. So we have different areas, and with this instrument, using Logger Pro, we can measure the angle that inclines. So the drag force is proportional to the angle. You can make a free body diagram. So that could be a good question to explore. How is the area affecting drag? Good for aviation, good for many other things. Experiment 1. Experiment 2, here we have glycerin inside this tube here, and here we have different size of steel marbles, which we measure the independent variable as the diameter or the radius of the marbles. With a camera here, we drop different marbles many times, and we look at the terminal speed, Stokes law. This is A2. How is the radius of a marble affecting the terminal speed? That's a possible question. Experiment number 3, it has to do with rigid bodies. Basically what we do, we drop, always from the same height, we drop a mass, so we have the same input of energy, we let it go, and we can record the time, for example, that, or a video record to see the acceleration, for example, of the mass, depending on the size of the wheel. Will it change? The size of this pulley, will this affect the rate of change of velocity or the acceleration at which the wheel flows? That's another experiment. Has to do with rigid bodies. Experiment number 4, a very simple experiment. We have an oscillating system, simple harmonic motion. If we change the mass of a spring oscillating system, the period of oscillation changes. We add more mass and we measure the period of oscillation. Experiment number 5, we have a rotary motion sensor and we change the distribution of mass. So we change, as an independent variable, could be changing the mass distribution and giving the same impulse to this system. That means dropping weight from the same height, creating the same impulse, the same torque, the same gravitational potential energy becoming rotational energy. This is also high-level physics. Could be done by a standard level student, but you need to study the model. How does the distribution of mass affect, I don't know, the angular velocity, for example, with the same impulse? So your independent variable is the distance between these masses, or the distance from the mass to the center, and your dependent variable could be the maximum speed. The good thing about these sensors is that they give you very good data. So this is known as polarization. There is a law that connects the angle between two filters or polarizers and the amount of light that goes through them, right? So we could explore how the angle affects the intensity of light. So this is a light sensor. We can cover this whole experiment, we can cover it so we only have the influence of the light going through the polarizers, right? This is called Malus law. So how is the angle between filters or polarizers affecting the intensity of light measured with Logger Pro sensors? Okay, this experiment has to do with standing waves, C4. We will study this next year. It's a very interesting experiment. This is a vibrator that sends a wave that goes back and bounces back, goes back and forth, and creates a standing wave. The question here could be, how is the tension, which you can control here, changing the tension by adding more weight, affecting the frequency or the resonant frequency? How is the tension affecting the first harmonic or the second harmonic? You choose frequency measured here very accurately with a frequency meter, tension measured with weight. So tension and frequency. There is a law, there is a model. So if there is a model, we can predict results and we can compare if it's accurate or not, and how precise they are. This is a rigid pendulum, it oscillates. We can explore factors affecting, for example, the period of oscillation or the damping coefficient. This has to do with oscillations of a rigid pendulum. We can change, for example, the center of mass and looking at how that affects the period with good data, very good data, or how the center of mass affects the damping coefficient. And a good experiment that was done this year by Sudarshan, a magnet and an aluminium, which is not magnetic, right? This is called induction brakes. How is the angle or the velocity affecting the force that is creating an induction brake? Induction brakes is something we haven't yet explored, but we will see next year, right? But it's good to learn theory from experiments, so you can just explore it and understand it. This is very, very interesting physics. Experiment 9. Experiment 9 has to do with the motor effect. What we're doing here is we're sending a current through a wire inside a magnetic field. When a current goes inside a magnetic field, it experiences a force. We measure the current, we measure the field, and we measure the force. We measure the force using a balance, a digital balance. So how is the current affecting the force inside a magnetic field? That is also a very linear and predictable model. 10, here. This is a classic experiment that some of you have already done. So how is the amount of energy affecting the change of temperature in a liquid? Could be water, alcohol. So we measure with this joule meter, we measure the independent variable of energy, and with the temperature as probe, with logger pro and a temperature probe, we can measure the change in temperature for every interval of energy that we add to this. Number 11, it's the same as before, but instead of a logger pro, we have a classic temperature thermometer, and instead of water, we have a brass block of 1 kilo inside a copper block and a copper container here. We're measuring, we can measure power, we can measure temperature, we can measure current, voltage, or energy. This measures energy meter, so it measures energy, time, everything. How is the energy affecting the temperature of the block? Number 12, we have 4 meters of copper wire wrapped in a block. We have a temperature probe outside the copper wire and a temperature probe inside the copper wire, thermometers, not temperature probe. And we just increase the temperature of this block to increase the temperature of the wire. And with this, we measure through the wire the potential difference and the current. So how is the resistance affected by temperature? There should be a correlation between temperature and resistance, because Ohm's law is for constant temperature, but when the temperature increases, the resistance should increase with a certain gradient. So we measure with this very accurately the current that goes through the wire and the resistance and the voltage that the wire takes to throw that current. So we know the resistance and we know the temperature at independent variable temperature, dependent variable resistance. Easy lab to do. Number 13, we have a light source, we have a light sensor, and we change the distance. Very easy. How is the distance to the source affecting the intensity of light? I wouldn't do this, but it's a very easy lab to do, to gather data. There should be an inverse square law, so we linearize and we make a graph with the maximum minimum gradients and find something about the ratio between the intensity of light perceived at a different distance, right? As you move away from the source, the intensity should decrease. How? That is the question to explain. This is a very good idea also. We have, again, a joule meter. We can measure current, voltage, power, time, all of that. The student here asked, how is the resistance of a circuit at constant temperature with the same temperature? That means starting from cool resistance affecting the power input at constant voltage. So he kept the voltage controlled, always the same voltage, but he changed the resistance and measured the power that the circuit took. There is a very simple equation there that connects power with resistance. Number 15. Number 15 is just a very simple experiment with a temperature probe, and we directly measure with the energy meter. We directly measure the amount of energy as independent variable, and we record the temperature of water here. So we add water, we measure the mass of water, we keep it constant, and we do many trials where we measure the energy and look at the change in temperature, and the gradient should give us something about specific heat capacity of water. So in this experiment we have a motion sensor. It detects the positions of a rolling body. So this is rigid body, right? We record with Logger Pro, we record the positions in time, and we can determine, for example, the maximum speed before colliding, the maximum speed of a rolling body. It could be a cylinder, it could be a ball. It has to do with moment of inertia. It's rigid body physics, it's A5, high level physics. The independent variable here was the change of height. So how does the height affect the final velocity or translational velocity of a rolling cylinder? We have different springs. That means I'm changing the constant of elasticity, and I'm looking at how the period of an oscillating system is affected by the different constants of elasticity. And to do this, we will use a motion sensor. We put a motion sensor on the floor. It detects the position of the spring. It gives us the period as dependent variable. How is the K, the constant of elasticity, affecting the period of oscillation of five different oscillating systems, keeping the mass constant but changing the spring? This experiment, number 20, is just changing. We have the same wire, the same wires made of a certain diameter and a certain material, so we know the resistivity of the wires. And what we do is we connect 2 in parallel, 3 in parallel, 4 in parallel. So what I'm changing is, for the same length, I'm changing the total area. How is the area affecting the resistance of a wire? There is also an equation for that. This is B5. We will study this. So we measure voltage and potential and current. 17. This is B3. We'll be studying this also in class. So what they did here is they trapped an amount of air inside a conical beaker. They measured the pressure inside the air, and with this instrument they measured the temperature around the beaker. This is full of water, right? So they changed the temperature by adding more heat, and they were measuring how the temperature affects the pressure. Yeah? There is a law that connects pressure and temperature. So this is Boyle's law. We trapped a volume of air inside the bubble, and we changed the pressure, right? And we control pressure as independent variable, volume as dependent variable. Temperature remains constant, so Boyle's law is how the pressure affects the volume of an enclosed gas, air in this case, at constant temperature, right? You do 3 trials, you find the uncertainties, you linearize the information, and you get a gradient that should mean something. Here, a very simple experiment, very simple. Sometimes the purpose of experiments is that they don't work very well, or maybe that the uncertainty is too big, but then you can criticize it. But here we want to see in a lamp how the temperature of the lamp affects the resistance. We know that a lamp does not behave according to Ohm's law because the temperature increases. You can see that because you touch the lamp and you feel it hot, right? So there is a filament there. We are assuming that we are measuring the temperature of the filament, which is a very bad assumption. We're measuring the temperature of the glass, right? But we change the amount of voltage. So we change the temperature as your independent variable, and we measure current and voltage as your dependent variable. Is it the same? Does it change with the temperature? Right? Similar to that experiment, less accurate. Doppler effect, C5. Oh, it's not working. Okay, this emits a certain frequency of sound. What they did is they changed the speed and they measured the frequency as with Audacity in a laptop. They measured the frequency, so how the speed affects the frequency perceived. That's Doppler, right? This is a coil with a core. You can put the core or ignore the core. You can take this out, whatever you wish. This measures the magnetic field inside a coil. You know that when the current goes through a coil, it produces a magnetic field. So we want to know how the current affects the magnetic field. Is there an equation that connects current? We measure current, and we measure magnetic field with Logger Pro. So you see the importance of downloading Logger Pro into your computers, right?